Why does Python code run faster in a function? This piece of code in Python runs in, note, the timing is done with the time function in Bash in Linux. However, if the for loop isn't placed within a function, then it runs for a much longer time. Why is this?
Inside a function, the bytecode is at the top level, the bytecode is the difference is that store_fast is faster than store_name. This is because in a function, I is a local but at top level it is a global. To examine bytecode, use the dis module. I was able to disassemble the function directly, but to disassemble the top level code I had to use the compile built-in.
You might ask why it is faster to store local variables than globals. This is a Python implementation detail. Remember that Python is compiled to bytecode, which the interpreter runs. When a function is compiled, the local variables are stored in a fixed size array, not a dict, and variable names are assigned to indexes. This is possible because you can't dynamically add local variables to a function. Then retrieving a local variable is literally a pointer lookup into the list and a ref count increase on the PyObject, which is trivial. Contrast this to a global lookup, load_global, which is a true dict search involving a hash and so on. Incidentally, this is why you need to specify global I if you want it to be global. If you ever assign to a variable inside a scope, the compiler will issue store_fasts for its access unless you tell it not to. By the way, global lookups are still pretty optimized. Attribute lookups foo.bar are the really slow ones. Here is small illustration on local variable efficiency.
Aside from local/global variable store times, opcode prediction makes the function faster. As the other answers explain, the function uses the store_fast opcode in the loop. Here's the bytecode for the function's loop. Normally when a program is run, Python executes each opcode one after the other, keeping track of the stack and preforming other checks on the stack frame after each opcode is executed. Opcode prediction means that in certain cases Python is able to jump directly to the next opcode, thus avoiding some of this overhead. In this case, every time Python sees for_iter, the top of the loop, it will predict that store_fast is the next opcode it has to execute. Python then peeks at the next opcode and, if the prediction was correct, it jumps straight to store_fast. This has the effect of squeezing the two opcodes into a single opcode. On the other hand, the store_name opcode is used in the loop at the global level. Python does not make similar predictions when it sees this opcode. Instead, it must go back to the top of the evaluation loop, which has obvious implications for the speed at which the loop is executed. To give some more technical detail about this optimization, here's a quote from the cvil.c file, the engine of Python's virtual machine. Some opcodes tend to come in pairs, thus making it possible to predict the second code when the first is run. For example, get_iter is often followed by for_iter. And for_iter is often followed by store_fast or unpack_sequence. Verifying the prediction costs a single high-speed test of a register variable against a constant. If the pairing was good, then the processor's own internal branch predication has a high likelihood of success, resulting in a nearly zero overhead transition to the next opcode. A successful prediction saves a trip through the eval loop, including its two unpredictable branches, the has_arg test and the switch case. Combined with the processor's internal branch prediction, a successful predict has the effect of making the two opcodes run as if they were a single new opcode with the bodies combined. We can see in the source code for the for_eta opcode exactly where the prediction for store_fast is made. The predict function expands to if next_insta equals op, go to pred_hash #op, i.e. we just jump to the start of the predicted opcode. In this case, we jump here. The local variable is now set, and the next opcode is up for execution. Python continues through the iterable until it reaches the end, making the successful prediction each time. The Python wiki page has more information about how Python's virtual machine works.
If you want to support the channel, please consider subscribing.